Okay. Standard 10th, subject maths, chapter number 1, real number, part 4. Okay. In a previous video, we have seen the application of fundamental theorem. Okay. We have seen one application which is irrationality. Okay. To prove irrationality, how we prove that irrationality? By using the contradiction method. And we used one theorem. If P divides A square, then P divides A, where P is my prime number and A is any positive integer. Okay, let's move on to the second application that says whether the decimal is terminating or not. Okay, so without doing the long division method, we can directly say this decimal is terminating and this one is the not terminating. Okay. Now, before starting this topic, let's just quick revise what is terminating and what is non-terminating things. Okay. In a real number, you have already studied in a standard 9. Okay. In a real numbers, we know that there are two types of numbers. Either it can be a rational or irrational. Rational or irrational. A real number is nothing but a collection of all the rational numbers and irrational numbers. Okay. In a rational number, we can express a number in a P by Q form. Okay. P by Q form and Q is not equals to 0. Okay. Where P and Q are my integers. Okay. P and Q are my integers. So P and Q are integers. Okay. Now, irrational, a number, those numbers we cannot write in a P by Q form. Okay. All those numbers are called irrational numbers. Okay. Now, in this rational numbers, there are again two categories. First one is terminating. Okay. First one is terminating. Okay. What do you mean by terminating? Let's say one example. If you divide 12 by 2. Okay. So 2 6 are 12. Hence, I am getting the remainder 0. Okay. After getting the remainder 0, we cannot do further division. So, we can say that this is a terminating. Okay. So, it's terminate over here. Now, the second thing is non-terminating. But repeating. Not terminating but repeating. Let's take one example. Say 3 divide 10. So 3 3s are 9. Again I am getting 1. My remainder is not, I am not getting 0. So I am put point over here and again it's divide. 3 3s are 9. 1. Again it's not divisible. 3 3s are 9. Again I am getting 1. Again 3 3s are 9. 1. Again 3 3s are 1. As you can observe, my remainder I'm not getting 0. Okay. And as you can observe, my quotient is keep on repeating. Okay. 3.3333. It's keep on repeating. So one statement is that if remainder is keep on repeating, if the remainder is itself keep on repeating, as you can see in a first division, my 1 is repeating. In second division, my 1 is repeating. In third division, my 1 is repeating. Fourth division, 1 is repeating. If remainder is keep on repeating, then my quotient also keep on repeating. Okay. So this one we can write that 10 by 3 equals to 3.3 bar. This bar represents that this 3 is keep on repeating. Okay. So we can write this one in a P by Q form. Okay. Because we know that after this one it's keep on repeating. Okay. So we can express in a bar form. That's why I can represent 10 by 3 in a P by Q form. So the next one is a non-terminating but repeating. Okay. So all these are comes under a rational numbers. All are comes under a rational numbers. Now the second rule, irrational numbers. Irrational numbers. In that one, there is only one category, which is a non-terminating, non-repeating, non-terminating, non-repeating. It means my quotient, okay, my quotient is keep on repeating. Say if you divide 22 by 7, 22 by 7. So what will be the answer? 3.14, so on and on. That digits are not repeat. Okay, so we can say it's a non-terminating. If the digits were not repeat, okay, if the digits is repeat, we can write in a bar. So it's terminate over here. If the digits were not repeating, we cannot express the digits in a bar form. So we can say that this much? My 2 into 2 into 2 into 5 into 5 into 5. Okay, so can be expressed is 2 to the power 3 and 5 to the power 3. I have done the prime factorization. Okay, now we can observe one pattern over here. We can observe one pattern over here. If a digit, if I want to express in a p by q form, so for our easiness, if my decimal became in some power of, like in some power 10th power, so it would be easy for us to express this number in decimal form. Okay, it would be easy for us whether this digit is terminating or non-terminating. It means if my denominator is in the form say 2 raised to m, some 2 raised to m power and 5 raised to n power, it would be easy for us to express, or we can say it would be easy for us that digit is terminating or non-terminating by just seeing its denominator. Okay, so the theorem says, let x be a rational number whose decimal expansion is terminate. Okay, let x be any rational number whose decimal expansion is terminate. Okay, then x can be expressed in a form of p by q, where p and q are my co-prime, and a prime factorization of q is in the form of 2 raised to m and 5 raised to m. Okay, so where n and n my non-negative integers. Okay, now the theorem says, if, let's take one example, say a 13 by say 10, not 10, take 2 to the power 2. Okay, see, my x is a rational number whose decimal expansion is terminate. So this one is my x, 13 upon 2 to the power 2. Okay. X can be expressed in a form of p by q, where p and q are my co-prime integers. Okay, and prime factorization of q is in the form 2 raised to m. Okay, let's just make these things in a 2 to the power n and 5 to the power n. Okay, so the 13 into 2 to the power 2 is there. If I multiply 5 in denominator, so I have to multiply 5 in the numerator also. Okay, so I am taking the 5 to the power 2, so that I am getting the answer in some 10th power over here. Okay, I am getting 2. So it would be easy for us to express this number in its decimal form. Okay, we can express this number in its decimal formation we can say it's a non-terminating. If it would be like 13 upon 7 into 2 to the power 5. See, 2 is there, that is okay. We don't have problem with 2 and 5. But here is 7. We cannot say about anything in 7. So we can say this thing is a non-terminating. Okay, non-terminating. Okay, understood? The theorem says the denominator should be either in the form of 2 raised to n, 5 raised to m, or else say both. Okay, if my denominator is in the power of 2 raised to n, okay, so we can express this 2 raised to n in some 10th power like this one, multiplying and dividing with the same digits. If it's 5 given, only the 5, we can multiply 2 to the power something, and in a numerator again we can express that the same thing. Okay. See, we have the problem with the other digits. If in a denominator it comes any other digits, we cannot say it's a terminating. We can directly write it's a non-terminating. Okay. Otherwise, we can check the denominator if it's in the form of either of these three things. We can directly say that this digit is its decimal expansion is terminating. Okay, now let's move on to the next questions. Now, the question said 11 into 2 raised to 5, 5 raised to 2, and 7 raised to 2. Okay. Now look at this one. 11 divides 2 raised to 5, 5 raised to 2, and 7 raised to 2. See, this is my x. It's this. What about its decimal expansion? Can we say it's terminating or non-terminating? Yes. Okay. From this, see, we just check its denominator. 7 raised to 2. Okay. From this one, we can say it's a non-terminating. See, using the theorem says x decimal expansion is terminating if its denominator q is in the form of 2 raised to n, m raised to n. Okay. So here given is a 7 to the power 2. Okay. That's why. Now let's take one another example. Say okay, let's take this one example. Now, this example, what about its decimal expansion? Whether this one is a terminating or a non-terminating. What we have seen first, we just check its denominator. If there are any other elements other than 2 and 5, we can directly say it's terminating or non-terminating. But look at over here. In denominator 2, 121 is given. 121 is given. But our theorem says it should be 2 raised to m or 5 raised to n. Okay. No any other element. No any other element. are getting denominator in this form? If yes, then we can say if this number is a terminating. Okay, so 11 to the power 2 and 1 to 1, so it gets cancelled. So again I am getting 7, 2 to the power 5 and 5 to the power 3. Okay, so we can express these things in a decimal expansion. Okay, now look at over here. It might be one question arise that ma'am, how can we can write in its 10th power, because my 2 to the power 5 and 5 to the power 3. Here my 2 to the power 2, 5 to the power 2 remains to get this answer. So what we are going to do, I am just simply multiplying with 2 over here and 2 over here. Okay, then it's easy peasy for us to write these things in its decimal form. Okay, now exercise Exercise 1.4. Question number 1. Okay. Without actually performing a long division method, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. Okay. So we are just talking about that without performing its long division method. So the first question is 13 into 3, 2, 1, 5. Okay, now look at over here. The first step is, see, here it's not given in this form, 2 raised to 3 and 5 raised to 6. From this one we can directly say it's terminating or not. But here my denominator given in some digits. So my first step is, okay, now write its prime factorization. Write its prime factorization of whom? Q. Okay, write its prime factorization. And the second thing, check or say simplify. If it is possible, if it is anything which gets common in numerator and denominator, that's why we are writing the simplifying. So just simplify it. Afterwards, we can check whether it's terminating or not terminating, repeating. Okay, so first what we are going to do, just taking a prime factorization of 3125. So here we can write say 13. Okay, so it's in the 5th power. Okay, so I have done the prime factorization. So 5 to the power 5. Okay, so from directly we can say, oh, it's a terminating because no other elements were given, only 5. Okay, so we can write this thing in a form of 2 raised to n and 5 raised to m form. Okay, so 2 raised to 5. So 2 raised to 5. Okay, now I'm getting denominator. It's in the form of some 10th power. Okay, so we can say that this one is the terminating. This one is the terminating. Now the second example. Let's take, say, this one. Okay, 7 1 to 9, 2 raised to 2, 5 raised to 7, and 7 raised to 5. Okay, now look at over here. 129. Okay, and 2 raised to 5, 5 raised to 7, 7 raised to 5. It's a terminating or non-terminating? Non-terminating. After you can when you simplify it, you will not get 7 written over here. Okay, so we are just simply say it's non-terminating. Okay, because it's not in the form of 2 raised to m, 5 raised to m. Okay, understood? Now, similarly, you can do all this exercise. So your homework, exercise 1.4, question number 1. All the questions you have to solve. Now, question number 2. Question number 2. Write down the decimal expansion of those rational numbers in question number 1 and above which we have terminating decimal expansion. Okay, now it means, see, in the first questions we have just directly write it's terminating or non-terminating. Okay, here we have just done its prime factorization now. Okay, so in the next step, in a question number 2, I'm solving over here only. Now question number 2, I'm writing 13, 5 to the power 5. Okay, I have to write these things in its decimal expansion. So 2 raised to, I have to write 2 to the power 5 also and 2 to the power 5 also. Okay, now multiply these things and multiply this thing, whatever the answer comes, you have to put a point. Okay, that is its decimal expansion. Okay, so in question number 2, you have to solve like this way. Okay, in the first questions, there is no need to write these things. After the prime factorization, we can directly say it's terminating. Okay. Okay. Now the question number 2 you have to solve. Now the question number 3. Okay. The following real number have decimal expansion as given below. In each case, decimal, whether they are rational or not. If they are rational and of the form p by q, what can you say about a prime factorization of q? It means, see, so my question says 4, 3, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. There is no dot given over here. It means it stops over here. So we can say it's a terminating. Okay. Now the second one, the question second one says a dot over there. So we can say it's a non-terminating or it's a non-repeating because no elements are repeat itself. Okay. So first one is point 120, 1200, then 12,000. Okay, and so on. So no single elements are repeating. So we can say it's a non-terminating, non-repeating. The third question says 43, 12, 34, 56, 78 and 9 to the bar. Okay, it means bars itself says that elements are keep on repeating, it means we can say it's a non